All right, so next we have a substitution. Mark Kluger, Vice President with Market Solutions TRS Group, couldn't be here today, so we have another presenter from TRS Group, Cameron Quick. Cameron is a project engineer out of Tampa, Florida, and he's going to talk about thermal desorption of PFAS-impacted soil. So, all yours, Cameron.
Awesome. Thank you for the introduction. As Joseph mentioned, my name is Cameron Quick. I'm a project engineer with TRS Group. Started in 2022. Excited to share with you guys a little bit about what we've been developing in our thermal conductive heating process for PFAS-impacted soil remediation. And talk to you a little bit about the research and development that we've had going on, a few of the pilot tests that we've been able to conduct, why you should care, and who TRS is as a whole. So I appreciate your time today. We'll first start off with a question that I think has been addressed pretty well here at the forum of why you should care. Included this slide. You can see here on the screen there's 27 different firefighting training facilities in the state of Florida that a lot of people have touched on using this AFFF foam, thus leaving a lot of the soils potentially impacted by PFAS left behind. Obviously there's plenty of other sources for PFAS around the world and in the state of Florida, but this is a great starting point for just looking at what's around us and what TRS can do to help treat and apply some of these solutions as well. The TRS technology that I'm going to be presenting today is perfect for this type of problem in that we can treat in situ or ex situ, as you'll see through our pilot studies that we've conducted. This technology also works really well in any lithology it's applied to, as well as any mixture of soils with different construction debris, concrete, things of that nature. Before we get too far along, just wanted to stop and pause and thank some of the collaborators that we've had across the research and across the 3 pilot studies that I'm going to be touching on today, and specifically the most recent pilot study at the JBER military base up in Alaska. So you can see on the screen some of the collaborators. We really truly couldn't do what we do without some of these collaborators along our side. Specifically, I wanted to thank the ESTCP for funding these 3 pilot projects that I'm going to be speaking about today, and the Defense Innovation Unit as well for selecting TRS for the most recent project that we're going to be spending a lot of time talking about today as well. So a little bit about TRS's history. Started back in the year 2000, so we officially hit 25 years this year, which we're all really excited about. Completed 200 plus thermal projects up to this point. Our research and development for what I'm going to be speaking about today began in 2014 after we started to realize that CERT-DP was starting to fund projects related to PFAS remediation, as well as ESTCP funding projects in 2015 as well. This research was concluded and published in 2019 and a patent awarded in 2020 for this technology. You can see on the far right side of the screen the 3 pilot projects that I'm going to be speaking about today, all ESTCP funded, beginning with the Eielson project up in Fairbanks, Alaska, at a military base up there, Air Force Base, the Beale ESTCP project as well up in Northern California, and then finally the JBER ESTCP project alongside the Defense Innovation Unit as well, recently completed in 2024. Moving on, just a quick overview about what it is that TRS does and what thermal conduction heating is. I'll go ahead and just kind of start with our process up in the top left corner. You can see we receive power from any local utility that we're able to cooperate with and deliver that power to our power control units. We have several different power control units in our fleet ready for all sorts of different types of projects that are available out there. And then moving on from the power control unit, you can see those power our TCH heaters, our thermal conduction heating heaters. You can see 2 different types of soil in this figure here. You can see the excavated soil mixed with all the rubble, construction materials, concrete, all that kind of stuff, which would be our ex situ application for this technology. And then also the in situ source area as well, so just treating the contaminants right in the original location that they were treated in. One thing to note about the in situ source area that we treat, this technology specifically for PFAS remediation is specifically for vadose zone, just for the types of temperatures that we have to reach to volatilize PFAS in the soils and remove them. And another thing to note about TCH is it's great for a source zone solution, kind of going for some of those higher concentration areas, not really a technology for the parts per trillion types of applications as well. One last thing too is to note that this isn't a technology for the destruction of PFAS, but more for volatilizing the PFAS and removing it from the soil and placing it onto our granular activated carbon or other solutions that we often implement on sites. So you can see from the heaters, then we have all of our soil vapor extraction from there, generally trying to cool the vapors coming out of the pile as they're at extremely hot temperatures. And also looking to convert some of those vapors that are coming out into the liquid form. So you can see kind of up at the top, passing all the vapor form through our condenser blower, and then vapor phase carbon, and then discharging into the atmosphere, and kind of more towards the bottom, passing it through pumps, heat exchangers, and then liquid activated carbon as well before we discharge. Moving on, this slide kind of shows a little bit about what TRS generally treats. Towards the bottom, on the bottom left of the slide, you can see some of the contaminants that we're most often treating and what we were treating prior to the development of thermal conductive heating. Some of those TCEs, PCEs are really the bread and butter and what helped get TRS underway. But through our thermal conduction heating, we can reach much higher target treatment temperatures on the left that you can see there, and we can reach some of those other contaminants. Specifically on the right, you can see the carboxylates and sulfonates groups of the PFAS family, what everyone's really talking about, the PFOAs, the PFOSs, some of those things that EPA has really designated as some of the contaminants to really focus on. This slide here talks about a little bit of the findings from our research that was concluded in 2019. You can see that, so we started with PFAS-impacted soils in the 20,000 micrograms per kilogram range, brought that into the research lab, started testing the reduction in contaminants at different target temperatures. You can see that we really start to see good results around the 350 degree Celsius mark, and especially at the 400 degrees Celsius mark, kind of above some of those 99.9% reductions that we really like to see at these source zones. Moving on to some of the pilot projects where we've implemented this technology. The first pilot project that we underwent was the Eielson Air Force Base up in Fairbanks, Alaska. This project was completed in 2021 and treated a ex situ soil pile that was 134 yards cubed total volume. One thing to note is that the soil pile was excavated and we didn't have any part in the construction of the pile, didn't get to help with the design of the pile, that sort of stuff. Just got to bring in our technology and apply it to the excavated soil pile. And then the one at the bottom there is the Beale Air Force Base project up in Northern California. This project was completed in 2023 and was an in situ vadose zone application of this TCH technology. Both these projects really got put to the test with extreme weather, as you can imagine. In Fairbanks, Alaska, we were battling in the winter, treating in the winter up there, so battling ambient temperatures as low as negative 35 degrees Fahrenheit. And then at the Beale Air Force Base, also had record-setting rainfalls while we were there, so really put these heaters to the test for these first two projects. A little bit more about the layouts of these projects. Again, from the research and development, we were really targeting at least 350 degrees Celsius for the treatment areas to remove PFAS from the impacted soils here. Very similar equipment footprint, kind of as we mentioned, using condensers, blowers, activated carbon, some water tanks on site for storage. One thing to note about the Beale, the in situ treatment layout that you see off to the right, is we were able to get some baseline sampling in the original contamination location. And as some other presenters have mentioned, a lot of that contamination really is kept in that 0 to 5 feet below grade surface mark. So that was some important information to learn and verify. Kind of blowing up some of these pictures and taking a look at the sites themselves. Kind of below the cover in the top right are where our heaters are at. This is our Eielson Air Force Base, as you might have been able to tell with all the snow on the ground up in Alaska. There are 48 heaters, vertical and angled heaters installed in this ex situ soil pile, as well as vapor recovery, temperature monitoring points, everything installed in the soil pile. Some of our treatment equipment, blowers, condensers, carbon is all indoors, kind of in the top left up there. And then off to the left, cooling tower, and then the rest of the stuff you can see up front is all electrical equipment, our power control unit that we touched on, as well as some switch gears, breaker panels for power and auxiliary equipment, communication equipment, electrical safety, that sort of stuff. And then off to the right is our vacuum switch, just for monitoring to make sure we're extracting the vapors out of the pile as needed. Here's a blown up picture of our Beale Air Force Base. This was the in situ source zone that we were taking a look at. Again, very similar equipment. This one had 16 heaters, 5 temperature monitoring points, 5 vapor recovery points as well. We have our granular activated carbon, condenser, blower, all that kind of stuff. One thing to note here too, as we are treating very close to the surface, is we had aerated concrete installed, about 3 feet of aerated concrete as our insulation on site with an R value of 30, which really helps us keep those temperatures high, even close to grade surface there. So with the learnings from our research and development and our 2 first pilot projects, most recently this was our Joint Base Elmendorf-Richardson, or as I will refer to it for the rest of the presentation, JBER, our TCH layout here. This was a much larger scale than the first 2 projects, the first 2 being a little bit less than 150 yards cubed in total treatment volume. This one itself was 2,000 yards cubed, so really taking on a larger ex situ soil pile here. Similar equipment, sometimes had to double up on certain equipment just because of the overall size of the site itself. We were able to implement on this project some of the lessons learned from the first 2 projects. One notable thing from the project team was that the original ex situ soil pile that we treated, if you wanted to sample the soil, you would have to destroy the insulation, really kind of dig everything up to get into the soil. But because we were able to be there for the construction of the soil pile here, sampling ports were installed in the soil pile so that we could get intermittent soil samples from the pile itself. So I'm going to go through a few slides here just kind of showing the construction of the soil pile. This is something that engineers kind of got to nerd out about as we got to be a part of the process of the actual soil pile construction a little bit. You can see here we had to be creative with keeping the soil pile out of the elements, have a really massive tent here to keep the 2,000 yard cube soil pile, again, out of the elements, keep it dry, that sort of stuff. And then we begin constructing the soil pile. You can see here we have our silicone impregnated liner at the bottom, and below that we were able to install heaters, our TCH heaters below where we were about to install the soil pile as well. As you can imagine, it'd be difficult to find insulation that could withstand the weight of the 2,000 yard cube soil pile. So we went with what we knew and installed 16 base heaters below the soil pile. That way the heat transfer from the pile doesn't just go directly into the native soil up in Alaska that's extremely cold. So we began constructing the pile layer by layer. You can see here, most notably the heater casings being installed in the pile here. We had about 4 rows of heater casings installed, which varied from about 80 to 120 feet in length. The ending shape of this soil pile was somewhat of a trapezoid, so some of those longer heaters being at the bottom and then getting shorter as we move up towards the top. Went layer by layer. Off to the right side, you can kind of see those black pipes sticking out. Those are some of our sampling ports that I talked about for being able to grab intermediate soil samples from the pile itself. As well as we start to layer this, we started to insert our temperature monitoring points. The heater off to the right there, you can kind of see a very thin pipe as well. Those are our heater TMPs, our heater temperature monitoring points, just so we can be right next to the heater, really tell how effective we're being with the power application and just the optimization of heating up the entire soil pile. Cross-section of the heater itself and just a little bit more of the details on what thermal conductive heating actually is. Really what we're doing is passing a lot of current through a very resistive wire that you can see here in the cross-section. And the heater then heats the steel casing itself. As you can see, we have some stainless steel and carbon steel for the casing, and then the casing itself is then what thermally conducts the heat into the soil pile, radially heating the soil around it. You can kind of see in the picture in that bottom right, that was from our research and development, but these heaters get very, very hot, upwards of 1,000 degrees Celsius. So really the optimization of the heater spacing, depending on the contaminants you're working with, can start to be pretty important. Some final pictures of the pile construction. You can see they're starting to throw a little bit of the insulation on top of the pile here in this picture. You can see the heater rows, again, the base heaters at the bottom, and then the rows of heaters after that. And then in between, you can start to see our temperature monitoring points, which are generally located in a triad of the heaters. We want to make sure that the points furthest away from the heaters are also reaching the target temperatures as well. And then also you can see our vapor recovery points as well. The engineers on the project got to make sure that we were getting sufficient vapor capture at all points in the pile, so we were very happy with how it turned out. Final picture of just installing the insulation on site here. The insulation that we used on top was a mineral wool insulation, also with a R value of 30 on site here. It was very difficult for the project team to locate materials that could withstand all these high temperatures, but we're very excited with how all the materials withstood the duration of the project here. Speaking of the soil pile temperatures that we were able to achieve on site, again, just wanted to reiterate that our target temperature really was around the 400 degrees Celsius mark, but we're okay with reaching 350, that kind of range. You can see we greatly exceeded that here at JBER. You can see the duration too on the x-axis there. This project lasted about 90 days, which exceeded expectations by about 2 weeks, which the project team was super excited about. You can see a little bit of pause there right around the 100 degrees Celsius mark as well. That was due to the moisture inside of the soil pile. We really had to spend some time boiling off all that water. And then once the soil pile was rid of all the moisture, you can start to see the temperature shoot up right after that. It was about 10 to 15 degrees Celsius per day for about 2 weeks. And then for the duration of the project after that, it was about 6 to 7 degrees Celsius on average per day. So really, really excited with the temperatures we were able to achieve here. One thing to note is this graph is showing the average temperatures of each temperature monitoring point, which each has about 5 to 6 actual temperature detectors in there. So you're seeing the averages in there, which is why we kept going past the 400 degree mark, because we were really waiting for a couple of those temperature detectors to finally reach the target temperature. And then off to the left there, you can see our total energy used on this project, and then the overall volume of the pile itself. And we're really excited about the energy density we were able to achieve on this site. It was much lower than we were even expecting, and we were really excited about it. A little bit more on the temperatures that we were able to reach. Again, our contractual temperature goals here was we were hoping to have an average above 400 degrees Celsius with no sensor below the 350 degrees Celsius mark, but what we were able to achieve was, again, an average around 638 degrees Celsius with no sensor below the 440 degrees Celsius mark. So all the soil samples were tested with the EPA method 1633 and all PFAS analytes below or near the detection limits. And I'll just stop and pause too, because you can finally see the completion of the soil pile here. We have our final liner over it, keeping everything kind of intact, all the heaters hooked up, vapor recovery points. It's really a sight to see. So some of the soil results that we had on site, on the left you can see all the different PFAS analytes that we were testing for. And on the right, the laboratory detection limits that we were hoping to hit. Again, all the sampling done hit or was below the detection limits or just near. As you can see, we had a couple of them there. One thing to note here too is all samples that were taken out of the sampling ports were right next to a temperature detector, so we were able to compare and contrast kind of what concentrations we were able to achieve versus what temperatures we were able to achieve on site. A little bit more about just comparing the sites between one another. Again, just wanted to emphasize the overall size of the most recent JBER project being 2,000 yards cubed versus the first two, and then also the use of horizontal heaters on site when the other two had vertical and angled electrodes along with some other site characteristics. Summary of our results, again, really happy with the temperatures we were able to achieve at JBER, average of around 638 degrees Celsius. Post-treatment PFAS was at a great level. Energy use the energy density here was great. Again, if you're going to transport this soil offsite, you could use that energy pretty quickly, just bringing it to a lab or somewhere else. So we were very happy with the energy density on site here. So wanted to reiterate some of the advantages of an engineered soil pile. With the energy efficiency that we were able to achieve on site, a lot of it was due to the pile size optimization, being able to build it layer by layer, the way we did here, having the base heaters even on site. And one thing we wanted to emphasize too is that regardless of the organic material, anything that's also in the soil pile being concrete, which we saw a lot of in this soil pile, construction debris, things like that, doesn't matter. This thermal conductive heating approach is very simple and effective and can still reach those temperatures even with the soil pile having all that kind of stuff inside of it. So wanted to wrap around to what this means for the state of Florida. As I mentioned kind of at the beginning, this would be a great application for these AFFF contaminated fire training areas that we can see all around the state of Florida. Conceptual site model seen on this slide here being that you could excavate all these shallow soils in the wide range of area, put it all on top of the original source area, and we can just apply thermal conductive heating to this area itself. Finally, with this JBER project, alongside the ESTCP and the Defense Innovation Unit, we received a success memo from them opening TRS to easier contract with all federal agencies for similar projects in the future. Wanted to stress that this technology currently is commercially available. It's one that we've implemented all across the US and even Europe as well. Again, the heater spacing allows us to really target all these different contaminants and their boiling points or target treatment temperatures as well. So very versatile, simple, effective technology. And thank you so much for listening today. Contact information there if you have any questions or follow-ups. No questions about my shirt being the same as this picture though.
Hi, Robin Young, Eagle Environmental. You mentioned earlier that the vapors created in the thermal desorption would then be recovered and run through GAC. Did you do any vapor sampling to see what kind of concentrations you were pulling off of the soil pile? And how much did you run this one through GAC, and how much GAC was used?
That's a great question. I don't have how much GAC was used on site. We'll go all the way back to the slide. Yeah, at all of our projects, generally we have usually 2 to 3 vapor vessels on site, vapor carbon vessels on site. And we're continually monitoring throughout the project, what's the influent concentration, what's the concentration between them, what's the effluent concentration, all that stuff. Mm-hmm. And I would have that, I can get that information for you, how much carbon was used on site. We always like to take a look at the end of our projects if we end up using more carbon than we thought we were going to use, that sort of stuff. So I can definitely get you that answer.
Awesome. And then off the top of your head, do you know how often you were, that carbon was getting spent and you were having to change it out based on your effluent samples?
I don't know off the top of my head, I'm sorry.
Okay. No, you're fine. Thank you.
Yep.
What's the condition of the soil once you're extracting the vapors? What else is coming out with it? Do you have to augment the soil to make it usable soil again?
That's a great question. I know they've given this presentation at other conferences and similar questions have been asked. The answer that was given by our marketing team, I know, was that this soil isn't obviously the same as it was prior to the treatment itself, but would be great for something as like a filler, something where weeds can't grow inside of it, that kind of thing, especially as it's starting to cool down. But yeah, there was definitely a lot of other things in the soil, like oil in the soil. This was at a military base, so a lot of things coming out, impacting our GAC and equipment, all that jazz. So yeah, hopefully that answers your question.
A good presentation. So when when you start cooking, I understand the engineer portion of the soil pile is easy to manage. When you do in situ, do you have a requirement for like moisture in the soil, because you're literally cooking steam out of the soil? What kind of moisture that you require to see the minimum impact of your results? And then if you do in situ, how do you control that if precipitation out there is getting a sandstorm or something that might impact your result?
Good question. Generally for these, like I was mentioning, this technology specifically is great for vadose zones because we don't want the moisture in the soil to be able to reach some of these higher temperatures. The other technology that I mentioned when we're aiming for some of those kind of chlorinated solvents, that sort of deal, the electrical resistance heating, that we will add moisture to the soil. We'll never add more moisture to the soil than what we're pulling out. Obviously, we don't want to move the contaminants off-site, but that technology specifically needs moisture in the soil to heat up the ground. But yeah, in this case, we aren't adding any additional moisture to the soil. Thank you.
Very good. Thank you.